this somewhere, so I can get credit, so I can write terms.
As well as the department head?
He's not the department head, but he's like the professor for the research class.
All right,
So I talked to him. But anyway.
here's a series, n factorial over n to the n. How are we gonna find out if this thing converges or not?
Probably one of those tests.
Turns out that's pretty good. Sorry, I decided to do that as I was writing the title, so there you go. But let's take a look at what we know about. Okay, test for divergence. We could do that. Okay, it turns out the limit as n goes to infinity of a sub n equals 0. Okay, n to the n grows faster than n factorial. Okay, and I can demonstrate that to you, but for a second we'll go with take my word for it. But you don't have to take my word. Sorry, that was reading Rainbow. All right. So then what? Is it one of our recognizable series?
No.
Okay, I think chances are slim that we're going to be able to write a partial sum really well. Okay. Then we would go to, does this series have completely positive terms? Okay, it turns out it does. Great. So potentially we could use the integral test, except how am I going to write that as a continuous function?
What does the graph of n factorial even look like?
What?
What does n factorial even look like?
If factorial itself is not a function that can take real numbers, okay? It can only take integers. We've had to devise something else to take integers that works like factorial, or that takes real numbers. Anyway, and I'm not even very comfortable with it. I know it's called the gamma function, and that is as much as I know. Okay. So, based on my current knowledge, the integral test is out, right? Plus dealing with x to the x probably would be very fun. Can we think of a nice comparison? Or even a less nice comparison to do limit comparison tests? That's pretty much what I thought. It has all positive terms, so the alternating series test is no good. We also could throw absolute values around it, but then we're right back at the same place we started with, so that's not going to be very useful. So we need something else. Yeah? Okay, does that work?
Mm-hmm.
Hopefully I prepared your brain to learn that. All right. One thing that's actually really good when we have factorials is the ratio test. And the ratio test looks like this. There are no conditions. You can use ratio tests all the time. Why do you say this to me? Because if it's a geometric series or a piece series, or I can do a quick comparison to one of those, it's actually lots easier. Okay. But here's one of our two tests that we can. Now I say that, but one of the conditions is the test fails. So okay, right. So there is a bad side to this. Okay. So what we do for this test is we look at. I'm trying to not look at my notes and write this down, but I might have to look at my notes to make sure I get the wording all right. Okay. Okay. We're going to do the limit as n goes to infinity. Okay, so we're starting familiar territory here, of the absolute value of a sub n plus 1 over a sub n. And now I'm going to double check and make sure that's the way that goes and not the other way. Sorry. duplication memory only works so good. Okay, I got it right. Okay. And we're gonna call whatever the limit we get F. Okay? And we get three conditions here. If L is less than 1, the series converges absolutely. If L is greater than 1, I think including infinity, now I'm gonna have to look again. There's broad strokes, not details always. Yep, including infinity. So we'll write that, or then the series. Oh, okay. The series diverges. If L equals 1, the test is inconclusive. Now, one of my favorite mistakes that people make, because anyway, is that I see people on their exams do the ratio test, get L equal 1, and then write down it's conditionally convergent. I do not think that word means what you think it means. Okay, inconclusive means I can't draw a conclusion. And for an example, in fact, 3 of them. Okay? If I look at this series that you're familiar with, that we did yesterday, and what did we show yesterday with this series? It converges absolutely, right? Okay, quick. What's the limit as n goes to infinity of absolute value of -1 to the n plus 1 minus 1 over n plus 1 squared, all over -1 to the n minus 1 over n squared. Sorry, in here we said that it converges absolutely. We did that yesterday. Okay, this would be good practice playing with limits, right?
Yeah.
Okay, we got a fraction and a fraction, so one of the things we can do is sort of flip things around, right? And we would get the limit as n goes to infinity of absolute value of -1 to the n, and then this denominator would come up there, n squared over n plus 1 squared times -1 to the n minus 1. So here's my first fraction on the one on top, and there's my second fraction on bottom flipped over. Everybody good with that? Okay, if we take the absolute value, the negative ones just go to 1, right? Okay, so I'm really, and then the n parts are positive, So we're really looking at the limit as n goes to infinity of n squared over n plus 1 squared. And remember, I can't shortcut too much. But that's the same as n over n plus 1 quantity squared, right? Because I'm squaring the top and squaring the bottom, so I might as well just square the whole fraction. What's this limit? That's 1. Okay? And so the point is this limit is 1. Okay? We got absolute convergence though. Yesterday. Right? Ratio test is inconclusive. But yesterday we showed that this was absolutely convergent. Okay? We showed something about another series yesterday. We looked at the series from n equal 1 to infinity of negative 1 to the n over n. And what did we show yesterday about that series?
Condition.
Yeah. What if we do the ratio test? Probably my absolute values and my fraction bar shouldn't touch. Sorry. I'm not creating a new math symbol that looks like a capital H, all right? They probably shouldn't touch, but they are. Okay, it's the same sort of thing, right? Someday we'll get this right. Negative 1s, go to 1. N over n plus 1 is positive, and that also goes. Remember, ratio test is inconclusive. Okay, one last example. We didn't do this one yesterday. That series is that's a divergent series. It's the harmonic series, right? And guess what we get when the limit as n goes to infinity? I'm showing something. Oh, I got that backwards. So we have n over n plus 1. We can drop the absolute values because everything's positive this time. And that still goes to 1. So I have 3 series where if I run the ratio test, I get the limit equals 1. And the 3 series I know from other things do different things. One converges absolutely, one converges conditionally, one diverges. Do you see what we mean by inconclusive? Okay. Does that make sense? So if we're getting L equal 1, we gotta switch gears. Okay, we gotta go somewhere else. Because we really can't tell if L equals 1, what the heck is going on. Okay, right? There's 3 series amongst billions. I don't know how many series. Okay, let's run our example then. We do some fun algebra this time. Okay, this time, by the way, Remember with the limit comparison test, it didn't really matter which one was a sub n, which one was b sub n? Because all we were looking for is some finite number. Now we're looking for the difference between less than 1 and bigger than 1. So doing the reciprocal would totally blow you away. Okay, it would in fact lead you to the exact opposite conclusion. So we've got to make sure we get it right. We're doing the n plus 1 term over the n term. Okay. But let's take a look at this series I wrote down earlier. Real quick, before we dive into this, fun fact about factorials. A factorial fact. What is n plus 1 factorial over n factorial? Can you guess that we might get this once in a while from doing the ratio test? Well, what's n plus 1 factorial? N plus 1 times n times n minus 1 times n minus 2 and so on until we get down to 2 times 1, right? Everybody good with that? What's n factorial? N times n minus 1 times n minus 2. Yeah? If I divide, what happens? I get to slash off a lot of things. I don't really know why I slashed off the ones. It doesn't really matter. Because slashing things off is fun. N plus 1 factorial divided by n factorial is just n plus 1. Sorry, a lot of times I do that as n factorial over n minus 1 factorial. Then I just get n. Okay, but right, I just get that. If I'm doing a factorial divided by a factorial 1 less, I just get the first term. Right, because everything else divides. Okay with that? Cool. Great, so let's try the ratio test on this, given that fun fact. We're going to do the limit as n goes to infinity of absolute value of, we'll have n plus 1 factorial over n plus 1 to the n plus 1 Thanks. All that divided by n factorial over n to the n. Let's start with fraction division. Let's start with fraction division. Okay. When I divide that, I get Let me make one observation here as I continue to go. The absolute value is unnecessary in this case, so everything's positive. So we'll take the absolute value right now. That was hard. Okay. And then that'll divide away, and the factorial will kind of divide with it, right? And I'm just left with n plus 1. Because n plus 1 factorial divided by n factorial is n plus 1.
Yeah.
Okay. And that means then I can divide n plus 1 into n plus 1 to the n plus 1, and I lose 1 power. Right, this is n plus 1 to the first over n plus 1 to the n plus 1 power. So if I divide that, I'll just get n plus 1 to the n power. That good? Done flashing now. And I get n to the n over n plus 1 to the n.
Isn't that just one step?
What's that?
Isn't that just one step?
That is not 1. So the n over n plus 1 would go to 1, but the problem is my exponent's going to infinity at the same time. Now, I gave you this fact a long time ago when we started this chapter and had sequences. And maybe we need to remind you of this, but okay, first off, I want you to remember from not my class, when you didn't learn the Hopital's rule and you were learning about indeterminate forms, one of our indeterminate forms was 1 to the infinity power. Okay, so that's where we're kind of at right now, is an indeterminate form. And so we could take the natural log of both sides and do that. Not of both sides. We could take the natural log of this and sort of play with that and find the limit. Trying to think of another way to do this. I know there's another way to do it, and I know what the answer is. It's just like, how do I make you see it? Is that fair? The other fact that we had, and again, this, I did present to you this before, but you probably don't remember, because I don't know that it's come up again. If we have the limit of 1 plus 1 over n to the n power, that's e. Okay, sorry. That limit's pretty important. Okay. I want to rearrange the inside there. What happens if I get a common denominator? What would this first one go to?
N over n.
N over n. And then if I add that to 1 over n, I get right, and that still equals e because all I've done is change forms here. Right, and here I'll show it to you, but I'm going to use the instructor cheat, all right? I've changed 1 to n over n. And then I've added fractions with a common denominator. Okay? That's not what I have here, but what do I have here? I have its reciprocal. So 1 over 8. Is that clear?
Wait, could you explain that just one more time?
Okay, are we okay with this?
Yeah.
What I'm looking at down here is the reciprocal of this.
Oh, I see. So it's just.
So I'm getting the reciprocal of the limit. Okay, does that work? Hope that wasn't cheating too much. I am resurrecting this fact that, again, has been presented to you, but you've probably barely used and therefore barely remembered. I mean, there. Okay. So we remind you of that. But you can start to see why we might run into this again and again and again and again and again. Okay. Oh, we should make a conclusion. I'm not done yet, right? I did the limit. Now I just walk away. No, I have to answer a question. Does this converge or diverge? Absolute convergence is sort of meaningless, right? Because I have positive terms. So if it converges absolutely, that's great. Conditional convergence isn't really a thing for this one. But is 1 over e bigger than 1 or less than 1? It's less than 1, right? Because e is like between 2 and 3. So this is somewhere between half and a third. Good enough? Because that's all I really need to know. It's less than 1. So our series converges. If this was a series that had negative terms, our conclusion would be that it converges absolutely. Again, here that's not overly meaningful. But okay, questions about that? Feel like it's a little bit easy to get lost in the details? Right? I mean, I almost walked away with the, I got a limit, great, I'm done. Okay. All right, let's take a look at another one. Dan. Then we should probably do a ratio test. Oh, sorry, root test. This is the ratio test. Okay. Both of the series I have written down right now have only positive terms. All right. All right, while you were writing that down, I sort of tried to mentally do a test for divergence. Okay, we've got this part that sort of is like 10/4 to the n power. Okay, which seems like, hey, that's geometric-ish, that would not converge. Plus, if I run the limit as n goes to infinity, I've got something bigger than 1 going to an infinity power that's going to infinity. But I also have this 1 over n plus 1. And that goes to 0, right? And so just on the mental side, right, I'm at an indeterminate form. Okay, so 0 or infinity, I don't know, you know, which one wins, or does it land somewhere in the middle, you know? So I don't know. The test for divergence has failed me, at least on the mental side. I would have to work a little bit harder at it. Okay, I'm not going to. I'm going to do the ratio test. Sound good? But I also feel like that tells me, and again, I think the comparison test, let's see, what would we have? With the n plus 1, we would be smaller than a divergent series. Does that make sense? If we compared it to 10/4 to the n, a geometric series that diverges, we might be able to do a limit comparison test on this one. Fair enough. I'm still going to do the ratio test because we're learning the ratio test today. This is a good example. So, okay. One of the things we have to watch for is this is not a factorial. Okay, and you'll see several factorials as you do the homework, but this one is not a factorial, and so we can't get carried away into treating it like a factorial. Okay, so we just have to keep that in mind, right? If we do the ratio test, we're going to do the limit as n goes to infinity of the absolute value of 10 to the n plus 1 over n plus 1 plus 1, so n plus 2 there, and then 4 to the n plus 1, and then all that over 10 to the n over n plus 1 times 4 to the n. By the way, just let me, after my little spiel about test for divergence, do you have a guess on which this does? Converge or diverge?
No.
No, you guys, okay. One person does diverge. I would think that's a fair guess. Right, because we're fairly similar to a geometric series that diverges. I would have to run the limit comparison test to see, right? But I don't know. That one might actually fail. You might get 0. Oh, that stinks. Anyway, let's do. We'll keep doing this. Okay, we're going to take the absolute value and do fraction division. By the way, you see how fraction division plays a part in a lot of these? If you want to start with like this step, where I've done the fraction division, I'm not gonna have a problem with that. Does that make sense? Okay, and then for this particular one, I've taken the absolute value now, everything was positive, so it didn't change anything. Okay, but again, if you want to start on this step on your homework, like, I'm okay with that. If that's not going to be super helpful, go ahead and write this out. Okay, what do we have that divides?
Tens.
Okay, the tens, right? I have n tens here and n plus 1 tens there. So I end up with just 1 10 to the first power in that place. Okay, and then same with the 4s, right? I have 4 to the n plus 1 power, 4 to the n. The n 4s here will divide with n of the 4s there, and again, I'm just left with 4 to the first power. Bless you. I don't think that, all right, the n plus 1 and the n plus 2 can't divide. So, all right. Let's see, the 10 is on top, 4 is on bottom, and then we have n plus 1 over n plus 2. And yeah, sometimes I randomly throw parentheses in, but I don't really need them. I mean, I could do this now, can't I? Okay, what's that limit? 1. Okay, so this is 1, the limit, but then I multiply by 10/4, right? So I end up getting overall 10/4,
Yeah.
which, hey, is bigger than 1. And so the series diverges. I'm still not sure how the test for divergence would turn out, but I'm not like super surprised either. Okay, we only have 10 minutes left, so we better learn the root test as well. You don't use the root test quite as much as you use the ratio test. You use the ratio test a lot. Okay? And we did it 5 times. Okay, right? And now, we did it 3 times on purpose because it was inconclusive. 1, 2, 3. Okay, but we're still working through the ratio test. Okay, and those 3 were inconclusive, and that was to show you that it really is inconclusive, right? Converges absolutely, converges conditionally, diverges, but we got 1 every time. And then we did 2 more times, once here and then once there. So we did a lot of examples there with the ratio.
Yeah.
Okay, good.
Hopefully it's not.
That's right. Hopefully it'll stick till you finish procrastinating your homework.
Yep.
which really should be like today. Today you should start doing ratio tests and root tests. Even if it's just like one or two. That'll help firm this up in your brain at some point. Root test. Look, that's, I'm gonna rewrite this. For the root test, we're gonna look at the limit again as n goes to infinity of the nth root of the absolute value of a to the n. Okay? We're gonna get a limit there, we'll call that L. We actually have pretty similar conclusions, in fact, the same conclusions as the ratio test. Okay? So, if L is less than 1, the series converges absolutely. If L is greater than 1, the series diverges. And if L equals 1, the series, the test is inconclusive. Or the test failed. Again, we don't have any conditions on this. We could run it any time. Okay. Now, one quick note to save yourself trouble. If one of the ratio or root test fails, the other does as well. So if you do the ratio test, you get L equals 1, don't do the root test, you'll get L equals 1 as well. Okay? These are helpful for when we're dealing with series with terms that everything is raised to the n power. Okay? If we don't have that, then we get ourselves a lot of times into some of our indeterminate forms for limits with exponents. And those were the worst ones to get out of. So maybe don't put yourself in that position. Anyway, okay. But if I have terms that everything is raised to the nth power, then the root test is great. Okay. Because I can get out of one of the exponents and then I can hopefully not have an indeterminate form that I have to struggle with. But you don't necessarily see a ton of series like that, so that's why we don't use this as much. Okay. So, as an example here, we'll look at, I have the series from n equal to of negative 2n over n plus 1 to the 5n. I will note that with negative 2 to the 5n, I'm getting an alternating pattern. Because I'm going to have a negative 5n is going to be alternate between positive and negative, depending on what n is. And then negative 2 to that pattern, will also alternate between negative and positive. So we maybe could do an alternating series test on this. But again, I'm going to do the root test. Okay, so I'll show you an example of the root test. Okay. If we did the alternating series test, though, we would end up with we would have to see if that's decreasing and if that goes to 0. Okay? So that would be check. Honestly, I don't think that goes to 0. That goes to like 2 to infinity. This is gonna diverge. I'm pretty sure. But let me show you an example of working the root test. Again, you know, what's nice about this one is everything is to the n power, and so if I do a root, then I knock that n power out, and so then I'm dealing with something a little bit more tame. Okay? The absolute value of -2n over n plus 1 all to the 5n. Okay, almost everything there is positive except for the -2. If we take the absolute value, that'll be +2. Okay, so this would equal the limit as n goes to infinity. The other thing is my nth root here will knock out the n part of the exponent. Okay, is that clear? Okay, so I'll end up with 2n over n plus 1 all to the 5th power. Okay, what happens to the inside of that? As n goes to infinity? It just goes to 2, right? And so our whole limit would go to 2 to the 5th power.
Right, how come it goes from -2n to just regular 2n?
Because I did the absolute value.
Oh, gotcha.
Even if we don't know that 2 to the 5th is 32, we do know that 2 to the 5th is bigger than 1. And so this diverges. Okay. Any questions there? Okay. Can I do anything useful in the next 3 minutes? Think so? Let me say something about what we've been skipping here. That's in the book. I don't know that it's in there. I'm not sure it's in this section, but one of the things that they do talk about in some sections in this book is, right, can we figure out what it converges to? Or if we can't quite figure out what it converges to, can we at least have some idea of how close we are? Okay, and so they call those error estimates. 2 of the error estimates that I'm confident are in here, and because I've had to teach this class where they didn't do those, is the integral test. With the integral test, you can do an error estimate. So you do your partial sum and say, okay, for the first 500 terms, here's what I got. And then you run the integral from 501 to infinity, and that gives you your error estimate. Okay? And then you can tell at least how accurate you are. Okay, or at least have some idea of how accurate you are, right? The other one that's kind of fun is with the alternating series test. Your error estimate is if you take the nth partial sum, so say again, I'm adding up the first 500 terms, my error estimate, which isn't necessarily fabulous, but is an easy error estimate to get, is the 501st term. Okay, right, and it's that back and forth that's going on with the alternating series that gives me that as the error estimate. Anyway, that's one thing that sometimes we're concerned about, especially if we don't know what these converge to, but for some reason we need to kind of have some idea. And I'll show you why we might need to do that as we deal with power series in a couple days. Anyway, again, that's something that's in the realm of something we call numerical analysis, which is things like how do I evaluate integrals that I can't do algebraically or do with our normal methods. How do I add up sums of infinite numbers? And lest you think this is completely useless, one of the ways we started getting better and better approximations for pi, as pi goes on forever, is by starting to create better and better power series, or power series that zeroed in on pi faster and faster. And so we might have originally known some that, you know, if I add up the first 10 terms, now I've got, you know, 1/100th of accuracy, woohoo. Okay, that's not very fast convergence, and so we started creating ones where we could get 2 or 3 digits a term. And I know that because I did a research paper for my senior project on calculations of pi. So anyway, so using these kinds of series can help us sometimes estimate if certain numbers. If we can prove that it converges to, you know, pi or something like that, then we can start adding up actual partial sums and getting an estimate for pi. Okay, and we've calculated pi to way more digits than we'll ever really need, other than to, you know, prove our calculators, our methods are good and our computers are awesome. You know, like that's what it's all about now. It turns out in the 80s, by the way, a calculation of pi showed that, you know, some big supercomputer had a major error in it because it didn't calculate correctly after so many digits or something, and so it revealed this big error in a supercomputer. And so I don't know. So it's still useful in that sort of sense, but yeah, we don't need that many digits to get the kind of accuracy we need for most of the stuff we're doing. So anyway, there you go. There's a little bit about why these might be relevant.
I have a YouTube video saved that's like to my watch list. Let's see how we found E.